Good morning, friends. Welcome to Traffic Protection part number 3, that is Segment Routing Ti-LFA. This is one of the most important topic for the segment routing, that is topology independent loop-free alternate. So in the part number 1, I talk about the rsvp-frr, how exactly it works, its configuration, and pros and cons. In part number 2, I talk about the IP-FRR or loop-free alternate. So there I talk about the basic IP-FRR, then Remote-LFA, how exactly it works, how it calculates the P and Q routers, and then discussed about the configuration part and pros and cons. So today let's deep dive into the topology independent loop-free alternate. While designing the Ti-LFA, developers consider the good points from the rsvp-frr, from the IP-FRR, and then they leave out the bad points from these both and have some additional features in the Ti-LFA. So let's talk about those one by one. So what are those good things Ti-LFA acquired from the rsvp-frr? That is link and node protection, sub 50 millisecond repair time, and pre-computed repair backup path in the forwarding information base. So what about IP-FRR? It's very simple to implement, just a single command and that's it. It is very scalable if we compare with the rsvp-frr because it don't need to maintain any signaling or don't need to maintain any states on the routers. IP-FRR is the ECMP aware backup path, and then leave out the bad stuff from the IP-FRR that was no signaling. For the Ti-LFA, it is completely local to the routers. We don't need any signaling between the routers. We don't have path protection option in the Ti-LFA, and no need to maintain any states on the intermediate nodes. And what about the IP-FRR? If you remember the part number 2 where we talk about the IP-FRR, it is completely topology dependent. But if we talk about the Ti-LFA, it is completely topological independent loop-free alternate. It provides the protection for all the topologies. IP-FRR, most of the time you will get the suboptimal repair path, but that is not the case with the Ti-LFA where all the backup paths are going via the post-convergence path. Separate FRR and post-convergence path, which is not the case in the Ti-LFA. Ti-LFA provides 100% protection, but it is with the help of loop-free alternative. It is the extension of the loop-free alternate. It supports the IP and LDP traffic as well, which is non-segment routing traffic. If we talk about the difference between IP-FRR and Ti-LFA, let's say the primary path from P1 to P7 goes via P3, P5, and then IP-FRR path goes via the P6, that is via the suboptimal paths. So if you remember the calculation, how exactly it figure out, The distance between next hop and destination, in this case it is 100, should be less than distance from next hop to source plus distance from source to destination. This is 3. So yes, in the case of P6 this condition is valid, but you might be thinking why you didn't choose the P4 as a backup path. So let's calculate and let's see why you didn't choose the P4 as a backup path. The distance between next hop to source, this is 3 plus 1, that is 4, should be less than distance from next hop to source, this is 1, plus distance between source to destination, this is 3. This condition is invalid here. This become kind of ECMP scenario, but it should be this value always should be less than this value. Thus the reason P4 is not the best alternate path for the IP-FRR in this diagram. So that is the one of the challenges with the IP-FRR, that most of the time you get the suboptimal paths for the backup path. This is the post convergence path. And then if we talk about the Ti-LFA, it always considers the post convergence path as a backup path. Let's see in the subsequent slides how exactly it calculates those stuff. Before deep dive into Ti-LFA, let's compare the coverage difference between LFA, Remote-LFA and Ti-LFA. So here I have increased the matrix so that all the prefixes should go via this path which we are trying to protect. So all this R4, R2, R5, R6 and R3 is going via this path. So we should get the coverage for all the prefixes. Let's see how the coverages are. This first is for the loop free alternate, per prefix loop free alternate. Here we are getting the 93.75%. If we go further, if we implement the Remote-LFA, we get the 100% here. And this is the case for the Ti-LFA. In the case of Ti-LFA, we always get the 100%. That's the reason if you check this show cie-sp route and then I'm matching this backup path, so it's saying that all path has loop free alternate. You might be getting confused here, but let's cover that into the subsequent slide, how exactly it calculates the Ti-LFA backup path. So as I said that Ti-LFA is the extension of the loop free alternate, and to enable Ti-LFA we need to first enable the per prefix loop free alternate, and then second command is for the Ti-LFA. So let's say we remove the per prefix the loop free alternate command from the configuration. So in that case your Ti-LFA won't work. So you can see here percentage coverage is 0. So to implement Ti-LFA, you must have the per prefix loop free alternate enabled. The benefit of Ti-LFA is that it is completely local operation to the node, and it always provides the 100% protection. And we can have the link, node, or SRLG protection based on the requirement. It always gives the backup path as a post convergence path. We don't have challenge here like what we have with the IP-FRR, where most of the time you get the backup path via the suboptimal paths, and it can protect the non-segment routing traffic like LDP and IP. So while providing those coverages, we can have no extra segment, we can have one segment, and max to max means 2. So while calculating those backup path via the post convergence path, router figure out the P node, and to reach that P node it use the prefix-sid. It calculates the PQ node. To reach that PQ node it calculates the prefix-sid. It uses the prefix-sid, and to reach Q node it uses the adjacency-sid. We will see in the examples, coming examples, how exactly to use those prefixes and adjacency-sid on the node. So let's see, we have configured Ti-LFA for this particular interface and we are protecting that. So this debug is running on the PE1. So first it will start with the per prefix loop free alternate. And in this case, it has selected the PE2 as a backup path for loop free alternate. So let's calculate again how it is. So distance from next stop to destination, it is 1 plus 1. So by default metric is 1 on all the interfaces. 1 plus 1 2 should be less than distance from next stop to source, that is 4, plus distance from source to destination, this is 3. So yes, this condition is valid here. So why not for P4? Let's see. So distance from next stop to P4 to destination, it is 3 plus 1 4, should be less than distance from next stop to source, this is 1, plus distance from source to destination, this is 3. So this condition is not valid in the case of P4. Hence you can see the per prefix backup path is going via the PE2. Then now it runs the RLFA. Now it's run the RASPF for the node P3, but it rejects that as saying that egress is the same interface. And now it's run the RASPF for the P4, but it's not the LFA router. And then it completes the LFA operation. So first it's run the LFA, then it's start with the Ti-LFA. So it has started the Ti-LFA operation, starting the operation for P2, but we don't have Ti-LFA enabled for the interface between P1 and P2. So it says that not configured for node P2. If we talk about the P4, this interface is also not enabled for Ti-LFA. So here it says that not configure for node fit P4. But this is the interface which we have configured the Ti-LFA. So it started the processing Ti-LFA processing for link between PE3, PE1 and P3. This is that interface, and the required algorithm is linked. So by default it is link. So for node and SRLG we need to enable it. Then it's starting the Ti-LFA link protection for node P3. So how it calculates that it's removes this link, and then PE1 runs the SPF once again to find out the next best available, or we can say that post convergence path. And once it figure out that okay, post convergence path is via this node or this link, then it tries to calculate the P space and Q space for the P1 and P3. So you can see in this scenario P1 and P4 both are in the P space, but PE5 not in the P space or not in the extended P space. P3 is not in the P space, not in the extended P space. Again PE7 is the not in the P space and not in the extended P space. So based on that one, it has calculated that PE5 is the next Q node. So this has become P node and this has become Q node. So all these routers are part of the Q space of P3 or destination. Then based on that, routers are going to figure out the SID. As I said earlier, for P node, router is going to use prefix-sid, and if you want to reach to Q node, it's going to use the adjacency-sid. So you can see here for P node, it is the explicit null, hence it is not showing any label here. But for Q node, it has figured out the adjacency-sid between P4 and PE5. So this is the case. P4 is become as a P node, where we are using the implicit null because it's directly connected to PE1. PE5 become the Q node, where we are using the adjacency-sid for that, and this is the SAP entry for that one. So if packet is living out of the backup path, it's going to have these many labels. First one is implicit for P4, second one is the adjacency-sid between P4 and PE5 allocated by P4, and then last one is the prefix-sid for the PE7. So these are the general steps. So first, router is going to run the SPF for all the prefix, that is using the rsvp for each neighbor. Once that is finished, router is going to start the Ti-LFA for the protected links. So it will see that which algorithm router needs to use, whether it is link and node, or link node SRLG. So it will bring down this particular link, it will remove this particular link, and then it's try to run the SPF. Once it find out the post convergence path, then he tries to figure out the PQ or PQ nodes. If LFA path is going via the post convergence path, it keeps the same. But if LFA path is not going via the post convergence path, sorry, here it should be post convergence, they need to replace with the Ti-LFA. What does it mean? Let's say from P1 to P7 LFA path is going via this way, but the post convergence path is this way. So Ti-LFA will replace this LFA path with the Ti-LFA. But let's say LFA path is going via the same path, and post convergence path is also going via the same path, and then Ti-LFA also has calculated the same path. So most of the time it keeps the loop free alternate path. Let's jump into the PQ node call calculation. So I have covered this portion in detail in the part number 2, that is for the IP-FRR. So if you need more information, you can visit that video. So it has covered in the RFC 7490. Let's see how it calculates based on the diagram. So what is exactly the P space? If we talk the P space of the router 1, so it is this P space or the routers which router 1 can reach easily without going over the protected path. So if we calculate if we run the SPF, so let's say this is the SPF for the router 1. So in this scenario, this is the SPF graph for the router 1. If we remove this link, so router can only reach to the R5 and R4. So this will become the P space for the R1. Extended P space. So PLR router will see that to which routers his neighbor can reach without going over the protected path. So R5 can reach to the R3 without going via the protected path. So if we say that default matrix is 1, so let's say here 1 1 2, but if he wants to go via this path, then its matrix become 3. So R5 can reach to 3 easily, hence it's become the extended P space for the R1. So we can say that P space and extended P space is this one for the router 1. Q space. Q space will be always for the merger point or for the destination. So it is always same like what we discussed in the case of P space. It is the space for the router 2 where he can reach without going over the protected path. So router can reach to the 3 and 4 without going over the protected path. If we talk about the SPF tree or graph for router 2, this is router 1, this is router 2, this is router 5, and then this is 3 and this is 4. So if you remove this particular link which is protected, a router can have reach till R4. So this has become the queue space for router 2. Let's discuss it on using more diagrams. So let's say this is the diagram and we are protecting the link between R1 and R3. So for R1, if we calculate the SPF, if we run the SPF, this is the SPF graph for the R1. And if we remove this particular link, so this has become the P space for the router R1, R2 and R4. These are in the P space of the router 1. If we talk about the Q space for the R3, if we run the SPF for R3, this is the SPF graph for it. And if we remove this particular link from here, then R3 can reach till R4. So this has become the Q space for R3. To find the PQ node, so this is the P space for the R1, this is the Q space for R3, and we can see that R4 is the common in the P space and Q space. So that node is become the so that node R4 is become the PQ space, PQ node. What is the extended P space? So it is on the behalf of the immediate neighbor, where he can reach to the routers without going over the protected link. So in this case, R5 is become the extended P space for R1. So we can, if we talk about this one, this is the extended P space for the R1, and this is the Q space for R3. So in this case, P R5 and R4 become PQ node. Let's talk about more using this diagram. So if we talk about the P space of the R1, if we run the SPF, this is the SPF graph for the R1, and this is the P space for it. R4 and R5 are in the P space of R1. If we talk about the Q space, let's run the SPF for R2. So this is the SPF graph for R2, and this is the Q space for R2, which is R3, R6 and R5. You might be thinking, why not R4? But R4 has the ECMP path. You might be thinking, why not R4? But R4 has the ECMP path via this node and via this node. Means it can send the packet over the protected link or via this link. Hence, it is not considered as a part of queue space. So R5 is become the PQ node here. So that's it about the PQ node. I'm hoping that you got good idea about the PQ node, because that is the core concept for the Ti-LFA. So for Ti-LFA, as we discussed earlier, that we can have multiple segments over the backup path. It could be 0, it could be 1 or 2, but it is very rarely that it could be more than 2. So let's discuss all this scenario one by one. So in this case, this particular link is having high metric, and then primary path is going via this P3 and PE5. We have enabled the prefix-sid and then Ti-LFA here. So this is the backup path for the prefix, and in case if that protected link goes down, then PE1 is just moving the traffic over the backup path without pushing extra level. Because generally to push the label for the queue space, we use the adjacency-sid. So in this case, P4 become queue space. So P1 needs to push the adjacency-sid, but it is directly connected, so it knows the adjacency-sid and it not going to push as it is directly connected. Hence, he is going to use the same label and it's going to send it over the backup path because it knows that once it reaches to P4, P4 has the shortest path towards the P7 and can push it easily towards the destination. Hence, we don't see any extra segment push over the label. That's why we call it as a zero segment. So you can see here it has calculated the LFA for that going via this particular interface. So it is just pushing the means it's just swapping with the same label. It's not going to push any extra label on the backup path. As we discussed in the previous slide, we are protecting the link between P1 and P3, and the link between P1 and P4 is the highest matrix. So P4 become the queue space of the P3 or P7 destination, and P1 himself acting as a P space. So as we discussed earlier that in case if it is the queue space, then we push the adjacency seed label on top. But as you can see here, it is directly connected, so he's not going to push any additional label while forwarding traffic on the backup path. So let's configure it and let's see. So this is the router we are going to protect, and this is the link between P1 and P4. So first we need to enable the per prefix LFA, and then second we need to enable the per prefix LFA Ti-LFA. That's it. Only these two commands are required to enable the Ti-LFA. And let's commit this configuration. So before that one, just let's check the routing table. So you can see that we don't have any protection. As we can see in this show ISIS fast route summary, we don't have any protection. So let's commit this configuration and let's see. Yeah. So we got the protection for almost 3, 4, 5, and 7 prefixes. So just check for the destination 7. So here it is saying that backup path is via the local LFA. Backup path is loop free alternate. And if we check this safe entry, it says that label impose is 16007 that is the destination label, and we don't see any additional label on top of that one. Let's check the debug for this. So first it was running the per prefix LFA for the no for the router R7, and in it then it started calculating the Ti-LFA, but it is saying that okay, the per prefix FRR path is going via the post convergence path, so we are going to keep the same path as a backup. So here it is saying that keep local LFA backup. This for the single segment example. In this scenario, it is going to push the one label, one segment on the backup path. So if we talk about the P space for the P1, so P1 and P4 are part of the P space. And if we talk about the extended, so it's reached till R6 because P4 can reach to R6 without going via the backup path. Hence it's become the extended P space. And this is the Q space for P3 or destination. So R6 is become PQ node. Hence P1 is just P1 will just push the prefix-sid level for R6, and from there R6 know how to reach to the R7 via the shortest path. So as we discussed earlier, if it is P node, we are going to use the prefix-sid. If it is P node, it will be prefix-sid, and if it is Q node, then we use the adjacency-sid over the backup path. So as this is PQ node, so it will be prefix-sid for backup path. So if we talk about the show ISIS fast reroute for this destination, so it's saying that this is the PQ node and this is the extra label we are going to push on the backup path. This is calculated using the Ti-LFA, and algorithm is link protection. So this is the original label for the P7, and then P1 push the extra label 16006 on top, and he will just forward it over the backup path once it detects the protection link failure. So P4 will just doing the penultimate hop popping and just forwarding the 16007 to P6, and P6 is going to push it over the shortest path towards the P7. Because here we are just pushing the single label here, that's why we call it as a single segment Ti-LFA. So if you check the SAFE or fib output, here it says that repair node is R6, and it's going to impose the two label on the packet 16006, 16007. Here all the links are default cost. The only link between P4 and P6 is having metric of 3. So we are going to protect the link between P1 and P3. So P4 and P6 will be the part of the P space, and P3, P5 and P7 will be the part of Q space. So let's enable the fast route for the link between P3 and P1. So this is the link which we need to enable the protection. Pass-through route per prefix. Pass-through route per prefix Ti-LFA. Before that, committing that configuration, just check the routing table. So we don't have any backup path for any prefixes. If we check the entry for the destination R7, and here it is saying that we have no protection. So let's commit this configuration and let's see. So we are committing this configuration on PE1. Let's check the routing table. Yes. So we got LFO for backup path for most of the prefixes. If we check the entry for the destination 7, so it has said that yes, backup path is via Ti-LFA and repair mode is P6. If we check the SIP entry, repair node is R6, and as we discussed earlier, it's going to push the 16006 for the P6 and then destination, that is 16007. So as we discussed in the earlier slide, that P4 and P6 is under the P space, but P6 comes as a part of the extended P space. And then P3, P5 and P7 and P6 are part of the Q space. So here P6 is become PQ node, hence you can see the prefix label 16006 for that, as per this diagram. So P1, P4 and P6 are the P space, and P3, P5, P7 and P6 are part of the Q space. Hence P6 become PQ router here. So if you check the ccie-sp pass-through route for the R7, should say the PQ node here because P6 is acting as a PQ node, and this is label it's going to push on top of that. So if you check the log for that debug, so it is calculating the per prefix LFA for R7, and then it's calculating the Ti-LFA for that R7. And it's updating that entry into the routing table. So let's shut down the interface between PE3 and P3, between PE1 and P3. The interface which we are protecting. Before that, let's start the tracer route for R7. And let's enter both at the time. So you can see that P1 has pushed the one extra level on top of that for the backup path. And this is the entry for the normal after running the SPF. This is the double segment where P1 is going to push two segment on top of the, and it's going to forward over the backup path. So this is the P space for P1, P1, P4 and P6 or R6, sorry for the typo. And then P3, P5 and P7 are part of the queue space. So if you remember earlier, I talked about if we want to reach to the P node, we are going to push the prefix-sid, and if we want to reach to the Q node, we are going to push the adjacency-sid. So on this backup path, we will have the two extra label. One is for the R6, that is 16006, and second label will be the adjacency-sid label between P6 and P5 allocated by the P6. So prefix-sid for the P node and adjacency-sid for the Q node. So if you check the show as fast reroute for this particular prefix, you can see that P6 has become the P node and he's going to push the 16006, and PE5 is the Q node where we are going to push 24003, that is the adjacency-sid label between the P6 and PE5. So this is how it looks like. 16007 is the original label for the destination. 24003 is the adjacency-sid between P6 and PE5, and then 16006 for the P node. Hence we can see here two extra label has been pushed on top of it for the backup path. That's why it is we call it as a double segment. If we check this SAP output, you can see here it is imposing two extra level along with the 16007, and then repair node it is showing as a P6 and PE5. Very rarely you will get more than two labels in your network on the backup path. It generally happen in case of the asymmetric link cost in the network, but it is very rare. This for the double segment. So here we have increased the cost between R6 and R5. So P1, P4 and P6 are part of the P space, and P3, P5 and PE7 are part of the Q space. So P6 and P5 both are acting as a P and Q router respectively. So as we discussed earlier, that for the P node we use the prefix-sid, and for Q node we use the adjacency-sid. So P1 is going to push two extra label on top of that P7 prefix-sid label. So on the backup path, we will have the bottom label as the prefix-sid for P7, that is 16007. Second label will be for P6, that is 16006. And then top level will be the adjacency-sid label between P6 and P5 allocated by the P6. So let's see in this lab. So this is the interface we need to protect. we have already enabled the Ti-LFA for that. So let's check the entry. So here we can see that Ti-LFA is enabled for the prefix, and these are the repair nodes, that is P6 and P5. Let's check this save entry. These are the repair nodes, and these are the labels P1 is going to impose, that is 16006, 24003 and 16007. Sorry, as earlier I said that second bottom label will be 16006, but that is not the case. Top level will be 16006, then second label will be the adjacency-sid between P6 and P5, and then last level will be the destination node prefix-sid, that is 16007. Let's check the show ISIS fast reroute entry here. So we can see that P6 is acting as P node and P5 is acting as a Q node, and these are the two SIDs it's going to push on the packet. These are the two extra SIDs. That's why we called it a two segment Ti-LFA. Let's bring down the link between P3 and P1. So before that, let's check the trace route for the R7. So it is taking P3, P5 and P7. Let's commit this configuration. Let's bring down the link between P1 and P3 and let's see how it reacts. So in the first output, we can see that P1 is pushing the two extra label, that is 16006 and 24003. And then at the P4 penultimate hop popping happens and it removes this 16006 and this then forward the packet with this two label to P6, and then P6 removes the adjacency-sid label and push the packet to P5 with the label 16007, and then P5 does the penultimate hop popping and send the package to the destination. And this is the path after it's running the SPF algorithm. Let's talk about the loop-free alternate, node protection and SRLG protection. So if we talk about this topology, we are protecting this particular link between R1 and R2. And if we have enable the fast route, means IP-FRR and Ti-LFA, so by default it will be link protection, and in this case protection will be via R5. And these are the two commands we need to enable for that. Where the link between R5 and R4 is metric 100, and between R3 and R4 it is metric 150, and in remaining paths have the default metrics. So let's enable the link protection between R1 and R2. So for this interface gig 000, pass reroute per prefix and pass reroute per prefix Ti-LFA. Before committing, we can just do the few checks. So here we can see that we don't have any backup path or protection available, and protection is 0%. So let's commit this configuration and let's check. So we can see that we got protection for few of the nodes. So we are checking the protection for the R4. Let's check this SAFE entry as well. We can see that label is going to impose 16004. And as we saw earlier, Ti-LFA is unable. Tiebreaker is default because we didn't configure the tiebreaker. Link protection is unable, and you can see that we don't have Node and SRLG protection here. So by default, it works as a link protection using those two commands. And once this particular link between R1 and R2 goes down, then traffic will reroute via the R1, R5, R2 to R4. If we talk about the link plus node protection, so using this one we have enabled the link protection, and for the node protection we need to configure tiebreaker node protecting and index 100. So in this scenario, this will be the backup path because we need to protect this node. So it will go via the R1, R5 and R4. So if we check the configuration for the interface, we have added this fast reroute per prefix tiebreaker node protecting index 100. So in this case, the lowest index is preferred one. If we have multiple tiebreaker options, then lowest one is going to take the preference. So in this case, node protection will be the highest priority, and then link protection will have the lowest priority. So let's check the interface for that one. And here we can see that Ti-LFA is enabled, link protection is on, and then node protection is also on with the index value. So if we check the route entry for this destination R4, so we can see that backup path is with the repair node R5 and R4. So in this case, R5 is acting as a P space and R4 is acting as a Q space. So you can see that R5 is acting as a P space with the implicit null, and R4 is acting as a Q space with the explicit null. And if we check this SAFE entry, we can see that it's going to push the implicit null and then adjacency 24007 on top of that packet. For link and SRLG protection, this is for the link protection and this command is for the SRLG protection, and this is the SRLG configuration. in this case, these both links are part of the same SRLG group. Hence, router is going to figure out the backup path via the R1, R3, R5, R2, and then traffic will reach to the R4 over the backup path. This is for the link, node, and SRLG protection. Here we have enabled using for the link protection. This is tiebreaker for node protection, and this configuration is for the link protection. And this is the SRLG configuration. So in this case, because we are protecting this node, we are protecting the SRLG. So we will get the backup path via R3, R5 to R4. So it's the link, node, and SRLG protection. So if you see in the diagram, there's both link between R1 and R2, and R1 and R5 has the SRLG configuration. So you can see in this configuration, we have configured that group, and we kept that both interface under the same group. So if you check this command output, so these both interfaces are part of the same SRLG value group. Let's configure the SRLG protection. If you check the running configuration, so in the last node protection, we configured the node protection for the node R2. So let's add the SRLG protection as well. Interface give 000 and then fast route for prefix tiebreaker SRLG index. Let's configure it as an index 200. Let's configure the index 50 and then commit. Before that, just check the entry for this interface. So we can see that Ti-LFA is enabled before committing this SRLG configuration, link protection, and the node protection. If we commit this configuration and then check this output, show ISIS interface, gig interface. So we should see that SRLG, node protection, and link protection, all these three are enabled here. So as we discussed earlier, that the lowest index is the preferred one. So here SRLG will be preferred, then node protection, and last is the link protection. So link protection has the least preference. So if we check this entry for the destination, so the path is going via the R1, R3, R5, and then R4. So it is protecting the both link as well as the node protection here. So R5 is acting as a P space. That's the reason he is pushing this 16005, and R4 is acting as a Q space. That's the reason it is pushing the adjacency label 24007 between R5 and R4 generated by R5. So if we check this SAP entry for this, so here we can see that it's going to push the two labels here, 16005 and 24007. So these are two repair nodes. So it's very difficult to capture the actual movement as we did in the last lab, because to reboot R2 and capture those packets is very difficult here. Load balancing on the ECMP backup path. So if we have any ECMP path towards the PQ node or from the PQ node towards the destination, in this scenario router can load balance over the backup path. So if we talk about this particular diagram, so PE1 is the P node here because of this high matrix, and P4 is become the Q node. But from Q node to the destination, we have the ECMP path. One is directly connected to P5 and second one is via the P6. So router can make use of the both path. So let's say for the destination towards the P7, he is using the path between P4 and P5, and for the destination P2, he is using the path from P4, P6, P5 towards PE2. So from, if we want to go to the router 2 on the backup path, this is how it is taking R4, R1, P1 to P4, P4 to P6, P6 to P5, and then destination. And for the PE7, it is taking P1 to P4, P4 to P5, P5 to destination. Because in this case, Q node to destination, we have ECMP available and router is making use of it. So this is how your MPLS forwarding entry looks like. For the 16002 for the PE2, you have two paths. One is going via the 45.5 and one is going via the 46.6. And then for the prefix PE7, one is towards the PE5 and one is towards the P6. As we talked earlier that Ti-LFA can provide the protection for the non-segment routing traffic as well. It could be LDP or IP traffic. Let's talk about that.
Ti-LFA for LDP and IP traffic. So Ti-LFA not only works for the segment routing, but it works for the non-segment routing traffic as well, like LDP and IP traffic. Let's deep dive it further. So it can provide protection to LDP or unlabeled IPv4 or IPv6 traffic. To achieve it, some criteria we should meet before providing the Ti-LFA for the CLDP and unlabeled IPv4 traffic. The PLR routers which is providing protection should be the SR capable device. and the destination which are in the LDP domain should have the prefix-sid available in the segment routing domain. For unlabeled IP for our IP6, we don't need any prefix-sid for that one because anyhow it is unlabeled. Because if you trace, you will see that there is no packet pushing, MPLS packet pushing on top of that traffic, so it is completely unlabeled. So we don't need any prefixes for that. But for the prefixes which are available in the LDP domain, we need the prefix-sid available in segment routing domain. So it can be achieved if those destinations are SR capable and LDP capable as well, which is very unlikely, and we can achieve that one using the mapping server. So mapping server will advertise the prefix-sid entries for these non-segment routing prefixes, like which are there in the LDP domain, and then whole segment routing domain can use that prefix-sid for those prefix. And then last criteria is either it could be P, Q or PQ node. So these nodes should be SR capable. So to provide the LDP Ti-LFA protection for the LDP, we must need to follow all these three criteria. And to provide the protection for the unlabeled IPv4 and IPv6 traffic, we must need to follow the first one and last criteria. So this is the lab topology which I am going to demonstrate. So let's first talk about the LDP traffic. So in this lab, R1 is acting as a mapping server, which is going to push the prefix-sid label for the R6 and R7, which are available in the LDP domain. And then whole segment routing is going to use this prefix-sid. So there might be a question in your mind when to use the mapping server. So if my destination is in the LDP domain, then we need the mapping server. But if we are traveling from the LDP domains toward the segment routing domain, we don't need any mapping server requirement on the LDP side or either on the segment routing side. Only when it is required when we are moving from the segment routing domains to the LDP domain. In a nutshell, if destination is in the LDP domain, then only we need the mapping server. So this is the primary path from R1 to R7, and for the backup path R2 is acting as a P node. So this R1 and R2 is acting as a P domain, R3 and R4 is acting as a Q domain. So this is the backup path which is going via R1, R2, R4 and R3 to R7. So for the normal path, for the primary path, R1 is using the prefix-sid label 16007 for the destination R7. Once it reaches to R3, R3 is going to do the implicit null for that because it's directly connected to R7, and it's going to do the implicit null and forward the packet towards the R7. And on the backup path, If you remember our earlier conversation, for the P node we need to push the prefix-sid. For the Q node we need prefix-sid, and if it is Q node then we push the adjacency-sid on top of the packet. So in this scenario, first bottom label will be the destination label, that will be the 16007, and the second bottom label will be the adjacency-sid between R2 and R4, which is assigned by R2, that is 24 something, and then top level should be the label to reach to the P node. But in this scenario, R2 is directly connected to R1, so it will be the implicit null for that, and it's not going to push any extra label on top of that. R2 will remove the adjacency-sid label, which is assigned for his adjacency towards R4, and then R4 is just swapping the 16007 with the same label 16007. R3 will do the implicit null and is going to forward the packet to R7. So let's check in the lab. So this is the router R1, where R1 is acting as a mapping server for the destination R6 and R7. So here you can see that I have configured the index value for R6 and R7. So if we check the command for the mapping server, so both of these entries for R6 and R7 both are active. So here you can see the index value and the range. So in this case we are just assigning it for the /32 for the single router, single prefix, hence the range is 1 here. So if you check the segment routing table, we can see the prefix-sid for the all destination except R5. R1 is acting as a mapping server here, and if we check about the LDP neighborship, so here it is between R1 and R6. R2 don't have because it's completely segment routing domain. Between R3 and R7, R4 is completely the segment routing domain. R5 is non-MPLS, that is a plain IPv4, and R6 is having LDP with the R1 and R7, and R7 has the LDP with R6 and R3. We check the routing table for the prefix R7. Here we can see that backup Ti-LFA is pointing towards the gig 000, which is towards the R2. Repaired node is R2 and R4. So as we discussed earlier, R2 is acting as P node with the implicit null value, and R4 is acting as a Q node with the adjacency-sid label. And you can see this is here, it is Ti-LFA link protection. And if we check the safe entry for that, it says that for normal primary path which is protected, R1 will push the 16007, and on the backup path is going to push the implicit null adjacency-sid label between R2 and R4, and then bottom label will be the prefix-sid label for the destination, which is R7. If we check the entry for this particular label, it's saying that if we receive this label, push it the segment routing label, and then this is the backup path. Where it's going to push the implicit null 24003 and 16007 on the backup path. So if we check about the R3, which he has received the implicit null from the R7. So if we check the MPLS forwarding entry for that, it's saying that if I get the prefix at 16007, just pop it and send it towards the R7. This is how LDP protect Ti-LFA for LDP protection works. So we checked it for the prefix R7, and R3 we can check it for the R6. So it is going via the interface gig 001 towards R4, and repair node is R4 and R2. But if you check the prefix 7 here, you will not find any protected path. So in case if we protect the path between R7 and R3, even though it is LDP domain, but in case if we protect, but still we will not get the Ti-LFA path for that. So first reason is that it belongs to LDP domain, and second reason is that even though if we enable it, if we remember the criteria for that, P and Q nodes should be the SR enabled devices. So if we talk about this protection between R7 and R3, R6 will act as a P node and R7 will act as a Q node. But problem is that they both are non-SR enable. Hence we won't get any protection for R7 on R3, and same is the case for the R1 to R6. If we check the route entry for R6, we don't have any protection for that. This is it about the Ti-LFA for LDP protection. Let's check for the IP protection. Ti-LFA for IP traffic. So in this diagram, R5 is acting as a plain IP4. This is the primary path from R1, R2, R1, R3, R4, R5. And this is the backup path where R2 and R4 again is acting as a P and Q node. So if we talk about the packet flow from R1 to R5, it is just plain IP packet. And if we talk about the backup path where R2 and R4 is acting as a P and Q node, so this is the packet for R5. Then on top of that one, it will be the adjacency-sid between R2 and R4, and then implicit null label for the R2. R2 removes the adjacency-sid and forward packets to R4, and from R4 anyhow it is the unlabeled, so it's going to forward it to the R5. So if we check the route entry for R5, So this is the normal path which is going via the protected interface that is gig 0001, and this is the backup path which is going via the R2. The repair node is R2 and R4. They are acting as a P and Q node. So if you check this show ISIS fast reroute entry for that, R2 is acting as a P node and R4 is acting as a Q node. So if you check this safe entry, so for normal primary traffic we don't have any label because that is completely unlabeled traffic, plain IPv4 traffic. And on the backup path we can say that we are pushing the labels. First one is implicit null, second one is the adjacency-sid. So on the packet we can see the only one label, that is adjacency-sid label. So this is the trace route via the normal path, that is R1, R3 and R4, and you can see that is non-MPLS plain IP packet here. It's very challenging here to test the traffic via the backup path, because once we bring down the link between R1 and R3, it takes millisecond for R1 to run the SPF and then put traffic on the normal path. Normal new means we can say post convergence path. So it's very difficult to capture the actual Ti-LFA traffic here. Microloop avoidance in the segment routing. Why do we call this as a micro? Because it occurs for very few milliseconds. When any particular link goes down in the network and it comes back, so after a few seconds customer complains that he is not able to send, or he got the traffic drop in his network. So generally it occurs when there are topology changes in the network. It could be link down, link up, or any metric change event. And when there are nodes in the network which are very slow to converge, and those nodes are taking longer time to run the SPF and update the FIB table, but the other nodes are in the topology, they are fast enough, they done their SPF, they push that prefix in the forwarding table, and they start pushing traffic towards this node which is very slow. But this router is still figuring out, is still calculating, and in the FIB table it is pointing towards its old entry, so he is going to send it back to the node which has done his calculation. This way microloops or loops occur in the network. So this is the lab topology for today's session. So traffic is going from P1 to P7 to P1 via P5 and P3. And P5 is pointing towards P3 next hop, which is going via the gig 000. P6 is pointing towards the PE5 towards the interface gig 0001. This is how it works in the normal scenario. But let's see if we add link between PE1 and PE4. And in this network all nodes are fast, but P6 is very slow in the convergence. So P6 runs the SPF and it updates its forwarding table towards the P6 routers via the interface gig004. But P6 is very slow and is still running the SPF, so the entry is still pointing towards the PE5 via the interface gig001, and the traffic from PE7 to PE1 hits on PE5. So PE5 forward is based on its FIB table towards the P6, but P6 is very slow, still figuring out the base path, and FIB is pointing towards the old entry, so it forward backs to the PE5, and again PE5 forward backs to P6, and then there are temporary loop in the network for few milliseconds or seconds. So what we if we remove that link? So in that case, PE5 runs the SPF very fast, populates the entry towards the P3 gig00 interface, and traffic between P7 to P1 runs via PE5 P3. It works fine. But in case if there is any traffic hitting via P6, which is very slow, and entry is still pointing out towards the P4 old entry, and it sends the packet towards the P4, but P4 don't have any link between P1 and P4, and P4 has updated his table pointing towards the P6, and he is going to send it back to P6. P6 again sends back to P4, and there are microloop in the network. So it happens when there is link up, link down, or metric change even in the network. So this debug I have captured it on PE7. So here it is detecting the event, that link up event has happened in the network, and then it start the SPF with segment routing microloop. He is saying that link between P1 and P4 is up. He figure out the P and Q node, and then build the auto MPLS traffic engineering tunnel, push the traffic over that tunnel with the extra labels, and then start the RIP delay timer for 5 seconds or 5000 millisecond, and it push that particular traffic engineering path information to the FIB level, so that traffic can go via that traffic engineering tunnel, where he is trying to push the extra label on the packet. Once this timer is over, then routers remove that traffic engineering tunnel information from the FIB and push the normal path information. So this is how microloop avoidance work in the network. So this is the auto tunnel which the source node built to reach to the destination node, and he pushed the extra label based on the P and Q node, so that packet should not come back to the source in case if there is any microloop happening in the network. So this is how it built this tunnel between source and destination based on P and Q nodes. So here if we talk about the traffic engineering tunnel, he figures out that P4 is the P node and PE1 is the Q node. Knows that if you forward information to P4, definitely he is going to reach to the PE1 via the adjacency-sid. So P7 push these two labels on top of the packet and forward is to PE5. PE5 just swap it with the P4 label and forward it to P6. P6 does the penultimate hop popping, removes the top label and forwards the packet with adjacency label to P4. P4 removes the adjacency label and forward packet to the PE1. This is just for the temporary purpose, just for 5 seconds where that RIP delay timer has set. And once the delay timer expired, then traffic goes as usual normal via the newly calculated path. So it pushed the prefix-sid for the P1, that is 16001, and then it gets swapped with the same level across the network, and P4 does the penultimate hop popping and forwards the traffic to P1. So this is the topology on the right hand corner side. If we check the routing table for the R1 from PE7, it points toward the PE5. If we trace route it, it goes via PE5, P3 to PE1 with the label of 16001. If we check the forwarding entry for that, it's saying that swap with the same level 16001 and push it towards the gig 001 interface, and next stop is the PE5. If we check the entry on the PE5, it's pointing towards the P3 via the interface gig 0003. If we check the MPLS forwarding entry, it says that swap with the same label 16001. If we check on the PE1, we don't have any agencies with P4. So let's run the continuous ping from PE7. The link between PE1 and P4 is the gig 000. So before commit, let's start the ping, and also let's start the route entry for 11 in case if we can capture that information. And on the P6, yes, we have committed that information. So let's see on the P1, it's pointing towards the P6, and let's see P6. Oh, but here we can see that we got two packet drop, because P5 was sending the packet towards the P6 and P6 sent it back to towards the PE5, and that's how loop occurred in the network. So when we committed the information at that time, P5 was pointing towards the P6, and if this is the information at the time of when it was running the SP upon P6, so it was pointing towards the PE5, and this is how microloops occur in the network. It's very remain for very short span of time. It could be millisecond or second. Let's configure the microloop avoidance for the ISIS for the segment routing and see how exactly it works. So under the IP address family IP4, it is just a single command, microloop avoidance segment routing. But to make it work, we need to configure the MPLS traffic engineering auto tunnel as well. So IP4 unnumber MPLS traffic engineering loopback 0, and then MPLS traffic engineering auto tunnel. It should be point to point, and then tunnel ID. Let's say minimum from 1000 to max 1999. So this is the requirement for the microloop avoidance. First, you need to enable it under the ISIS for the IP-FRR address family, and if you have IPv6 address family, you need to configure for that as well. And then we should have the MPLS traffic engineering auto tunnel configuration, because microloop avoidance uses the MPLS traffic engineering feature to force the traffic with the multiple level on the new path to avoid the microloop. So let's commit this feature. Let's run the enable the debug. Microloops avoidance detail, let's say detailed. So we have enable the debug. Let's shut down this link back. So it should go down. Just clear the log and configure the buffer so that we can capture all the packets. Let's see, let me enable 00. So now ISIS agency between P1 and P4 is down. So if we trace from P7, so it's going via the PE5 and P3. So before that, let's check the ISIS. Here it is saying that yes, microloop avoidance is enabled, and the rev update timer is 5 seconds. So if we check the safe entry for this prefix, it is pointing towards this particular interface. Let's bring up the link between P4. So here if you check the ISI status, here it is saying Microloop avoidance enable, rip delay timer is 5 seconds and state is active, link event link is up. So he has calculated near router is P4 and far router is PE1. And then MPLS, it brings up the MPLS traffic engineering tunnel to force the traffic with the two labels, that is 16004 and 24003 on top of the label, on top of the packet. So if we can see this shape entry for the prefix 1.1.1, so it is pointing towards the traffic engineering tunnel T1006. If we can see this output, show MPLS forwarding prefix 1.1.1.1/32. Incoming level is 16007. Outgoing is pop, because where we will add the level which assign for this tunnel, and outgoing interface is this tunnel interface here. So this is the trace route before enabling the link between P1 and P4, and this is the trace route when we enable the link between P1 and P4, we bring up that link, and here you can see that P7 is pushing the two label on top of that packet. One is for P4 and one is for P1, adjacency-sid between P1 and P4 assigned by P4. And if we trace the normal path again, because after some time we should get it over the via the normal path using the normal labels, it is 16001. This is the debug captured on P7 when we added the link between P1 and P4. So here it is saying that P4 to P1 event is link up with metric 1, and it's evaluating the added link between P1 and P4. So it's calculating the total metric here, and then it starts the SPF with the segment routing microloop for this particular event. So here it is trying to calculate the complete path, the P node and Q node. Here you can see that P node P4 is acting as a P node and P1 is acting as a Q node, and it's figure out the label, which label it needs to push on the top of tunnel. So here it's calculating the matrix and path, and it figure out the label. Then he tries to figure out the changes for P3 as well, but it says that P3 is not the far end, no processing for the link up event. And after that it pushes the traffic over the traffic engineering tunnel, but before that it starts the rip delay update timer as a 5 second. Then it push the traffic engineering tunnel information in the fib table. Here we can see one path updated with the traffic engineering tunnel, and then it downloads the information in the fib level so that traffic can push over the traffic engineering tunnel with these explicit labels. And after 5 second rip delay timer get expire, and then it removes the path from the forwarding table and forwards using the normal labels. Thanks for watching it, and if you have any query, please comment below. Thank you very much.